Okay, here we are back at the saddle. What I'd like to do is look at the 2 points P and Q on the saddle and talk about partial derivatives and a directional derivative involving them both. So you can see that I've labeled the point P. It's the point 0, and the z value there is -2, but the point P is really just the point 0, The point Q I've labeled as 1.40 with the z value being 2, but that really is the point just 1.40. Let's talk about the partial derivatives at P first, so I'm just going to turn off Q for a second. What I'd like to do is talk about the west-east chop at P. So let's do that. I'm going to drag this little point way over here and start walking from west to east. Well, you can see that the z values are very, very high way to the left, right? And as I walk east, it becomes smaller and smaller and smaller and smaller. So the time I get to P, the z values are -2, and then immediately they start getting bigger again. And what is that going to tell us? That's going to tell us, since we came down, 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 down to get to P, and then up, 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 up after we get to P, that it's a relative minimum. That's going to make the partial derivative there 0. A different way of seeing that is, let's just walk just to the left of P, due east just to the right of P. Because the contour goes very horizontal here, right? Walking just to the left of P and walking due east just to the right of P, we stay practically on the contour the whole time. If you're staying on the contour, z isn't changing, and if z isn't changing, the derivative must be 0. So that gives us two different reasons for concluding that fx at P is 0. Now, fy at P is much more conventional. I'm just going to talk about it briefly. You can see over in box 11, I have the little calculation. I picked a point just to the right. The height was about 1.8. I picked a point just to the left. The height was 1.2. And you can see in the calculation, it was just a change in the z's over the change in the y's. And we got about -3 1/3. So that's the end of our discussion of the partial derivatives at P. So I'm going to turn off P. I'm going to turn off, and I would like to turn on Q, I think. And there's Q. Now Q is going to be very similar, except with respect to Y. I'm going to turn on the south-north chop at Q. And I want to start very far south, where the z values are very negative. And as I walk north, you can see the z values rapidly becoming more and more positive. They become positive until I get to 2. And then as soon as I get to Q, I pass Q, the z values become more and more negative. Recapping, as I walk from south to north, the z values go up, up, up. As soon as I pass Q, the z values go down, down, down. That's going to make Q a relative maximum along that chop. If Q is a relative maximum along that chop, then Fy there should be 0. We can do the same kind of discussion we had before, however. If I go just south of Q and walk due north to just due north of Q, because the way the contour is shaped, you can see it's almost vertical there, right? As we walk from just due south to just due north, we pretty much stay on the contour the whole time. If we're staying on the contour the whole time, the z value isn't changing. If the z value isn't changing, the rate, the derivative in that direction, should be 0. So that gives us two different reasons, without really an explicit calculation, that the partial derivative Fy at Q must be 0. Now, another brief discussion about the partial derivative with respect to x. If we do a partial derivative with respect to x, I need a point due west, I need a point due east. You can see over here, I said that the point due west had x coordinate -1. The point due east had x coordinate 1.75. And you can see I made my little calculation here, and you can see that I calculated the slope roughly in that direction to be 2 2/3. The reason we're really here is that we want to take a chop from P to Q. So there's P, there's Q. I would like to turn on the chop and hope that good stuff happens. Now, there's the chop. Now, I label us green in this picture, so I'm going to start walking along the chop. As I walk along the chop, you can see the z value is becoming more and more positive until I get to P, then still more and more positive and get to Q, and then more and more positive after that. Again, it looks to me like as I walk along the chop that the z values are becoming more and more positive. I would expect the slope of the chop at P in that direction to be positive. Now here's the problem. If I want to chop in that direction and find a slope, I'm not going to use P and Q. Q is telling me the direction of the chop, but these points are so far apart, you can see how much differently, for example, the contours are behaving at P than they are at Q. So once I make the chop, what I want to do is go to P and find a point just before P on the chop that's on a contour, and find a point just after P that's on a contour, and that would be right here. I think I can turn those on. Let's just see if I can. Let's see, there's that, and that. And you can see I've labeled point B is the point before, point A is the point after. Let's see if I can make that work better, so we can actually see the points. Yay! Okay, now I can see point B, I can see point A, and what I'm going to do is find the rise over the run from point B to point A. That should give me a better estimate than if I just use P, and a much better estimate than if I use P and Q, since Q is so far away. Now, you can see that I've labeled B negative 0.4, 1.9, and the z value is negative 3. I've labeled A 0.4, 1.3, and the z value is negative 1. And what I need to do is do the rise over the run. Well, the rise over the run, the rise is easy, because it's a change in the z value from B to A. The z value at B is negative 3. The z value at A is negative 1. It goes up by 2. That's not a biggie. The problem is I need the distance from B to A. Well, we're not going west to east, so the distance isn't delta x. We're not going south to north, so the distance isn't delta y. We really have to find the distance in the plane from B to A, and we need to use the Pythagorean theorem to do that. So over in box number, looks like 33, you can see that I made that calculation. It's just going to be the square root of the change in the x value squared plus the change in the y value squared. And happily enough, we got 1, so I'm happy about that. So according to this graph, the distance from the red dot B to the purple dot A is really 1. So finally, if I want the slope in that direction, I need the rise over the run. And that, I think, should be 2. Because the rise was 2 and the distance was 1, and you'll see that over in box number 34. Whew. All done.